Hey everyone. So in this video, we're going to do a review or an overview of how vector embeddings work with a focus on text embeddings, right? So as you can see here, how you can convert words into vector embeddings, and similarly, how you can convert sentences, right? Which is what we care about, how you can convert them into a vector. So what is a vector embedding, right? So vector embedding is where you can take, in our case, a sentence and using what is called an embedding model, convert that into a vector, which, as we know, is a mathematical entity which consists of numbers. In this case, you see a collection of floating point numbers, and this entire vector, you know, kind of means something, right? It kind of represents a quantity, a property of an object, right? And so it's a vector and it's a vector embedding because it's constructed, right? It's not a natural vector where you have a set of numbers that are just arranged. You're creating using or constructing an embedding model that takes this and converts it into a vector. So typically these embedding models are machine learning, mostly deep learning models, right? And so you can think of it as, a way to take, in our case, say text, a sentence or a paragraph, and convert it or translate it into something which is a set of numbers. So math basically, right? And why do we do that? Well, if you want unstructured data and then you want a neural network to be able to process that, right? So you want a neural network like a language model or an image model. Um, then the neural network, as you know, only understands numbers, right? So how do you get that neural network to process text? Well, you convert the text into a set of numbers, which then goes into the neural network as its inputs, right? So if you were just solving, like we have done previously in different videos, just taking a set of numbers as the input data set, well, in this case, the text would become the set of numbers, which would be the input data set. You'd have the label, and then you'd pass it through the neural network. In our case, this video is part of a series where we're trying to build an email classifier, right? Well, how does the neural network understand emails, right? We've learned over the previous videos how these neurons work, how layers are. We've understood how the softmax converts the output of the last layer, or in this case, is the last hidden layer, into probabilities. We know how to train it. But how do we take the email and convert it into a set of numbers, right? Well, vector embedding model does that for us. Now, embedding models need not be just for text. You could have them for images, you could have them for audio, and so on, right? So it's basically a methodology that takes unstructured data and converts it into vectors, which can then be processed by neural networks. And so this embedding model is a very specific algorithm or a specific set of algorithms that are designed to give you vectors that actually have meaning, right? They have meaning and they're designed to capture context of the unstructured data, right? Because if you have, say, a set of images or a set of text, they mean something. You want the embedding model to be such that when it converts that into a vector, it actually captures the essence or the meaning that is embedded, right? That is there in the unstructured data or embedded in the unstructured data. So let's start with a simple example. We're focused here on text-based models. The simple example is to start with words, right? So let's say you have this word called laptop, right? Now let's say we have an embedding model, and in a few minutes we'll see how I got here. But let's say you can translate this word laptop into this vector. We've kept it simple. It's a two-dimensional vector, and so it's got laptop. Let's say is minus 1.16, 3.38, right? We can do this with other words as well. So what I'm going to do is get the two-dimensional vector, and that is the vector embedding of the laptop, right? It's a 2D embedding, so two-dimensional embedding. We can plot this on the x and the y axis. That's why I'm choosing two dimensions. So let's say you have laptop and I plot it. So this is what it looks like. Now let's say I have the word dog. So you see that and I've plotted that. So the embedding model that I've constructed is taking this word and giving me this as the output. Now I say cat and you see cat showing up. And so after cat, let me plot a few more words, right? So I've added a few more here. Now you see some fruits and vegetables showing up, right? You have mango, carrot, and coconut, right? We've also added books. So you see that I've created an embedding model, right? Just assume it's an interesting, correct embedding model. And what that embedding model has done has taken these words and converted them into two-dimensional vectors. And plotting that, we see how they cluster. Don't worry about what the values are, because in practice, you'll be using a different embedding model. This is just an example. But they're constructed in a way where, as you can see, words that are contextually similar cluster together, right? Which means the embedding model has captured the essence of these words. So you see that in this case, the fruits and vegetables are clustering together. You see that the animals, the cat and the dog, are clustered together. You see that, things like laptop and books are away from, the fruits and the vegetables and from the cat and the dog. But, the books show up closer to the laptop. You could think of it maybe as the model capturing the fact that both are used for learning, or both are inanimate objects, or both are used in the classroom, for example, right? So we see that embedding models capture the essence of words. And what's a good way to understand that? Well, let's look at Matt, right? So if you see Matt, is Matt closer to cat, right? Or rather, you have Matt, is cat closer to Matt? Or is cat closer to dog? So if you look at it just from a spelling standpoint, the C and the M are different, but the ATs are common, right? Whereas with dog, cat and dog have no common letters. Yet, when you create an embedding model, so if you just do a string search, cat and Matt should show up, right? They're more related. However, you use an embedding model and you see that cat and dog show up closer together and Matt shows up completely different, right? It's quite far away, right? So you see that a model like this, which is a vector embedding model for words, that we have constructed in this case, two-dimensional, but it's capturing the essence of these words. So now when you give this to a neural network, let's say, for some training purpose, it understands the context by understanding at least what words are related to each other, right? Now, we're looking here and saying these are similar, right? In practice, how do you compare these? So typically, to compare vector embeddings, we use what are called vector distances, right? Which is, as you can think, as the name suggests, just looking at the distances between the vectors. Now, there are different metrics that can be used to measure distances. So you have what are called the, just the Euclidean distance, which is basically the actual distance between the coordinates. So, and in this case, we've used a two-dimensional embedding. In practice, you would have embeddings that are much larger. So you would basically do this where A and B are the two objects. Let's say you have cat and Matt, and each of these subscripts indicate an index. So in this case, you just have A1 minus B1 square plus A2 minus B2 square, right? In practice, it would say, have 100 dimensions, and you do that for the entire, that all set of dimensions. This is called Euclidean distance, which is basically a way to get distances between 2 points in a vector space. And so you can use that and say, well, actually, the dog shows up closer to cat and Matt shows up much farther away. In practice, something that's used that's a better metric, especially in high dimensional spaces, is what is called the cosine similarity metric, right? And what that does is look at the angle effectively between the two vectors. So in this case, you'd say, well, is this angle, which is because Matt is here, is this angle greater or this angle? And this should be to the Matt, right? But I've not drawn the arrow long. So is this angle greater or is this angle greater, right? In this case, we see these two vectors are closer together. The angle is smaller, and so these vectors are closer together. So they are more similar. Matt is a completely different direction. So it's farther away from cat, right? So it tells you again in this case that dog is closer to cat than the Matt, right? And so this is how you compute cosine similarity. So we see that vectors capture context or the essence of words in our case, because it's a word embedding model that we're looking at, rather than just looking at the spelling, right? Our cat, dog, Matt being the same. And so this is called this enables what is called contextual or semantic search. So bigger picture, if you were using Google and you type something in, for example, it's giving you responses that are not just doing string comparisons. It's actually doing comparisons based on context. If you see the links that it gives you, they're actually contextually very valid, right? And so it uses embedding models, right, to try and understand context. And of course, if you've used large language model based tools of say ChatGPT, again, same thing, right? How does it understand what you're asking? Well, it needs a way to understand context. Now, a language model uses embeddings, right, for words. And then, of course, there's retrieval augmented generation or RAG, again based on this. Now, how did we get a 2D embedding? Well, I'll give you a rough idea, and I've modified this a bit to kind of get it to work. But the basic idea being you take the word, and I used what is called GLOVE, which is a word embedding model. So you can go check it out here at nlp.stanford.edu. And it's a very famous, widely used approach to get word embeddings, right? It's very easy to use. You can download the model and you can load it up fairly quickly. And the instructions are here, they're very clear. Now, we'll do a separate, kind of video on how GLOVE works as a course on vector embeddings. But just to give you an idea, so I took that and got GLOVE, and it gives you a 100-dimensional vector, right? And then I used what is called principal component analysis, which is a way to take a set of vectors and reduce them to the simplest, or to a smaller size vector that captures the essence of it. So in this case, I've reduced it to a 2-dimensional vector. And so depending on the vector set I have, it's basically trying to find a 2-dimensional coordinate axis that best captures the essence of these. And we see it does quite a good job, right? Even though I'm significantly reducing the size from a 100-dimensional to a 2-dimensional vector, you do see the context being captured, right? Okay, so you've understood how we've got that. Feel free to go and try it out. What we care about for our email classification is sentence embeddings. So word embeddings are helping us to do word comparisons, semantic search with the idea of words, and then language models are, of course, built on word embeddings, right? Different kinds of word embeddings, though, you wouldn't use GLOVE for that. You'd have a different approach. And we'll cover that when, if it's a course on language models. However, what we have here for our case is we have sentences like this, right? So we have, say, win a free iPhone 14 by clicking this link. And then you have, let's say, a different, email saying your subscription is expiring soon, renew now and save. Are these two related, right? Are they correlated? Are they not? So we need an embedding model that can capture the context or the essence of sentences, or if you're looking at bigger emails, paragraphs like these. And so you have sentence embedding models, which are again key for semantic search. They become extremely important in retrieval augmented generation, right, or RAG. Because now what you're doing is you have your own data, and you're now you're trying to compare a user's query with the data you have, pick out the relevant paragraphs, which you would feed to a large language model. Right? And then, of course, you have, in our case, what we're doing, which is data clustering and pre-processing. Right? So we have a set of emails. We want to convert it into vectors in a way that it captures the essence. So we'll see at the end of this video how our emails kind of cluster into interesting sets, and that then can be fed into a neural network for classification. So let's say a sentence like this: dogs love chewing on bones, right? How would we convert this into a embedding? Now it's an embedding for the sentence. Think about it for a second. So we've already seen how word embeddings can be computed. One approach could be, let's just take the embeddings for each of these words. You can average it, and you get your sentence embedding. As you can see, there are a lot of issues associated with this. You could have longer sentences and you would average, and then how do you know it captures the essence? You could have the ordering of the words being different. How does that get captured? You could have a word being used in different contexts, right? So you could have Apple, which is a company. You could have Apple the fruit, right? You could have bank, which is where you store your money, or a river bank. These are examples that are very commonly cited. And a word embedding model does not capture that. Typically, they are static embedding models. They have one vector for a particular word, right? So it becomes complicated when you have sentences. Models then got developed that began to use neural networks, right? And more specifically, recurrent neural networks, right? So the words would get fed in, and then the advantage of a recurrent neural network was it would capture context fairly well, right? But we live in the age of the transform. You don't have to worry how this works as of now. We have a full course on that. But transformers power the best, most powerful language models today, right? And so that applies for embeddings as well. And so what we're going to be using to convert our sentences into embeddings are sentence transformers, right? So the sentence transformers library is hosted on Hugging Face, right? So you can go check it out. And they have a lot of different kinds of models. The work was based, or the basic idea comes from this paper called Sentence BERT, right? Which uses Siamese BERT networks, right, to generate sentence embeddings, right? And so the repository is hosted on Hugging Face, but maintained by the UKP lab, right? The same people who've written this paper. How does it work? Well, it takes BERT, which, as we know, is a large language model, which is based on the encoder part of the transformer, right? And so what it does is, and the training is different. I won't go into the training. I have a separate video on that if you want to look for detail. And so I'll link that when that comes out. But the basic idea is a sentence goes into BERT, which returns, a set of vectors. Think of them as columns for the different words, right, in the sentence. So embeddings, which then passes through a pooling layer. And what you get then is the sentence embedding. Now, to get this, there is a training process that happens, which is what uses the Siamese network. I'm not explaining that in detail here because we're focused more on an overview and an understanding of the application, and it's a little complicated for our video here. But if you're interested, I'll add the link when when we have that video on that coming out. And so what happens is this model is basically trained such that it gives you very accurate sentence embeddings that capture the context of the words by training the model such that it's able to understand whether sentences are related. Right? Okay. So this is the basic idea or the architecture of how the SBERT model works. Now, while SBERT is available, but obviously a lot more advanced models using the same principle are now available. So what you can do is go and check out the MTEB leaderboard, right, on Hugging Face, and you have different embedding models that Hugging Face hosts, and you can see the number of parameters they have, the dimension of the model, and how good they are for different tasks, right? And depending on your task, you can pick. There are also other providers, right? So we're using Hugging Face. But there are other providers that also provide embedding models. It depends on what you're using the sentence embedding model for. So depending on your application, you can pick, right? In our case, we're going to pick the Paraphrase Mini LM L6V2. So it's a fairly simple, quick to run model, but it's good enough for our purpose, where it'll take an email and convert it into a 384 dimensional vector. So in our case, we've just got a one sentence email. It's for this class. So it's a fairly simple email, almost like the title of the email, which is what we're focusing on. So it's taking that and it converts it into this vector. So let's go now quickly, just practically implement this. The sentence transformers, it's exceptionally simple. So let's take a quick look at the code and then we'll come back. Okay, so we have a Jupyter notebook open. And this one is slightly different from the ones I've used in the previous video. We'll obviously eventually move this back into that notebook, but I'm just keeping it separate, right, from the previous notebook where we've added our neurons and so on. So to install the library, you can obviously go to the website on Hugging Face or Google Sentence Transformers, but basically you can use pip, right, and just do pip install -u sentence transformers, and that should be it. And then you can say from sentence transformers, import sentence transformer, and you've imported the model, right? I've also have a few more imports for this: NumPy, Pandas, and Matplotlib, right? So we're just going to do a quick exercise here. So as I showed you in the slides, we're going to pick the model. Now, there are a number of different models as we discussed, and you can pick whichever one you want. I'm picking the Paraphrase Mini LM L6V2. So all you have to do is say model is equal to sentence transformer, which we have imported, and give it the name of the model, right? So let's run this and run this, right? And it'll take a second and it should load that. Now what are we going to do? We're going to let's take a sentence. Let's say win a free smartphone by clicking this link now. Now if I want to generate an embedding for this, what do you do? It's actually really simple. Once you've defined the model, all you have to do is say embeddings is model.encode sentence, right? And what I'll do is I'll just put this actually in a list, right, just to make things easier, because you can give it a list of sentences and it'll work and that's how ideally you should do this. So I'm going to say sentence is win a free smartphone by clicking this link, and then I'm just going to run this, right? And so what model.encode will do is generate the embedding. If I give it one sentence, it would be one array. In this case, I've given it the sentence but as a list. So you see it's a two-dimensional array, and the first vector, the only vector, is this embedding, and this is the embedding, right, of this text we have written, right? So what's the size of this? Let's just say print len embedding 0, right? And you say it's a 384 size vector, right? So it's basically taken this text and converted into a vector of dimension 384. So what do we do with our email data, right? We have the data set for our email classifier. I've put it in a file called emaildata.json, right? And so what we can do is just open that as a file. And so we aren't actually using pandas here, and say data as json.load file, and then break it into two pieces, the sentences, right? So the text and the class. So let's just, let me just, print kind of what this would look like. So you get an idea of why I've done that as well. So let's just load this and say print data. So what it's going to be, the format we have our data in is, it's basically a JSON file where you have a list of objects, and each object has text, which is basically the text of the email, and it tells you what the class is, right? So this is the actual data, and this is the label. So sentences will take all the data, and classes will give you the labels. So when we have a neural network, now this will kind of convert this into a one-hot encoding and pass that into a network. This will need to convert into vectors. How do we do that? Well, we've just seen the answer to that. Very simple. All we have to do is say sentences is this, embeddings is model.encode sentences, and that's it, right? So we run that, and I can say print, right, len embeddings, right, and it's 192. There are 192 sentences, so it's going to give you 192 embeddings. We can look at the first one, and it should be the same as what we saw before. So we say print embeddings 0, you get the embedding for that, right? And there are 191 more such embeddings. So what we can do is we can do a principal component analysis like we did for our word vectors, right? Only now we're doing it for the sentence embeddings. So I've just created a color dictionary, right, which says spam, social media, work, marketing, important and personal, depending on the class. I've imported matplotlib here again. I don't need to do that, but what I can do is say from scikit-learn, which is a repository, a library in Python, which has a lot of interesting machine learning functions. I'm importing PCA, or principal component analysis. I'm telling it the number of components or the number of dimensions. In our case, I want to plot it, so I'm going to say 2, and then I'm just going to say PCA.fit and give it the embeddings, right, where we know the embeddings. And let me just take this out so that you see the code above. The embeddings is basically just a list of lists, a list of vectors, right, that you've got from here. So it's just going to take that in and give you a reduced embeddings. So what I'll do is, let me just move this to the next. Let's just print reduced embeddings, right? Okay, so let's run this, and you see now it's actually been reduced to a two-dimensional vector. So the large 384 dimensional vectors are now two-dimensional vectors, and now we can plot that, right? We can say xy coordinates are the reduced embeddings, and we're giving it the color scheme of this color depending on the class that it belongs to. We have the classes here. We've already set that up. Set classes is D class. So depending on the class, what we can do is this. So for I, C class and enumerate classes, basically, as you can see, takes out the corresponding index and the label. You now take x and y, which are the coordinates here, and you plot that, right, as a scatter plot. And then this is the size of the the dots, and then color is based on the color scheme, right? I don't want to annotate the sentence, it's just going to get messy. What I can do is just run this, and we see our embedding. So we see this being visualized. We have our color schemes here, so the label is not showing up, but basically you have spam, social media, work, marketing, important, personal. So you see, let's go back to the slides, right? You see this plot, I'll explain this in slides, right? You can see in the slide where I've got the label for this, and you can see how well they cluster. But we've seen now how you can use the sentence transformer library to generate embeddings for sentences, right? And we've seen an example of how you can use the principal component analysis to reduce this to a smaller dimension so you can visualize. Okay, so let's get back to the slides. When I again, take the embeddings and run a principal component analysis on that, we see how it works fairly well, right? It clusters the emails now into these data points, which in two dimensions, when projected into two dimensions, looks like this. You see the spam emails here. You see, as you can imagine, spam and the marketing emails coincide. You have the social media emails, slightly different, but again in that same area. The important emails show up here, and they show up in a way that they're similar to the work emails. And the personal emails, interestingly enough, some of them show up here, some of them, are closer to the work or the important emails. So you see how these cluster in a very interesting way. It makes sense, right? So now you could use a clustering algorithm to try and classify your email, but of course, we're going to try and now train our neural network on this data. So the next video, we're now going to put the pieces together. We've covered all these pieces over the last set of videos, and now we know how to take our input and convert it into a vector embedding. Let's now understand how the feed-forward neural network that will be trained to classify this, how that works, right? So let's start putting the pieces together in the next video. So see you in that.